Okay, so last video we talked about the meaning of electric potential energy and voltage. This time we're going to talk about a little more on potential energy. Particularly, I'm going to start by talking about the amount of energy it takes to assemble a configuration of charges. And then I'll talk a little bit about how to get the electric field if you already know the voltage. And then based on that, I'll talk a little bit about equipotentials. Alright, so from last time we had this definition here that the voltage at a position B minus the voltage at a position A, which we write as VBA, so it's basically the voltage to go to B from A, can basically be defined as a line integral minus the integral from A to B of E dot dl, okay? And one of the important things to remember is that because the electric potential, because the electric forces are conservative, the path that we take from A to B does not matter. We can take any path we want. All that matters ultimately is just the endpoints A and B. So if we're moving a charge Q from point A to point B, then the change in potential energy, delta U, going from A to B, is just defined as Q times the voltage difference between B and A. Okay, so it's a lot like how you get the force by multiplying the electric field times the charge. To get the change in energy, you just multiply the voltage by the charge. So then if we have a collection of charges and we want to define the potential energy at some point, due to this collection of charges, then basically it's just the sum of all the potentials. This is the potential of a point charge. And the important thing to remember here is that this is actually a scalar. Okay, so we don't actually care about any vector quantities here. All we actually care about is the distance, r sub I, which is the distance from, let's say, a particular point charge I to the position that we're interested in. And for a continuous charge distribution, it's just the integral of k dq over r. So this is just the continuum limit of this finite sum. And so here we're taking, and this is the convention we'll use, the potential at infinity. So when you're extremely far away from the charge distribution, we'll just call that potential to be 0. So that's our reference point. So when you're infinitely far away, the potential is 0. All right, so based on this, I'd like to talk a little bit about how we can go and get, let's say, the energy needed to assemble an arrangement of charges. So this should be pretty straightforward. So let's imagine I'm going to start by bringing in one charge. Okay, so we've got a charge here. This is the first charge we bring in. So we'll call this Q1, or charge 1. All right. And there are no other charges around. So basically, it doesn't actually take any energy to bring this charge in because there's basically no other electric field around except for what is generated by this charge here. And it doesn't feel its own electric field. So there's no other electric field around, so I can just bring this in from infinity, and it doesn't cost me anything. All right? But now this charge is going to set up some potential, right? So it's got a potential around it now. So now let's imagine I bring in another charge. Let's say, I'm going to bring another charge. I'll call this Q2, and I'm going to bring it over here, okay? And Q1 is nailed in place, so, it's not moving as Q2 is brought in, all right? So basically now I'm going to bring in Q2 to this point here. So, there's going to be some energy cost to bring this in. So basically, Q1 is going to set up some potential even before Q2 has been brought in. So then so basically, let's imagine I'm going to write the total energy needed to assemble this configuration. So U total, right? So there's no cost to bring the first charge in. To bring the second charge in, basically there's some energy cost, which is, I'll call that U12, which is basically going to be Q2 times the voltage that Q1 creates at this position where Q2 is sitting. All right? So I'll call that V1. I guess I'll call that at position 2. Okay, so that just means where Q2 is. All right, so let's imagine we bring a third charge in. Okay, so I'm going to bring now a third charge in, Q3. So first I'll just draw this here. Actually, I'll change the color. So this energy is just U12. All right. So now I'm going to bring Q3 in here. And so basically, as I'm bringing Q3 in, right, it's going to experience some electric field from Q2 and also one from Q1, right? And so basically there's some potential that Q3 is going to feel from Q2. I'll call that U23. And it's also going to feel some potential from Q1, which I can call U13. All right, so going back to this sum over here, so U total now is going to be U12. Now when I brought Q3 in, basically I basically have some energy term, which is U23 plus U13. All right, and then let's imagine I bring a fourth charge in. I'll stop at the fourth charge. So, here's a fourth charge. It can be positive or negative. It doesn't actually matter. I'll just make it positive again. So here's Q4. So now when I bring Q4 in, it's going to feel an electric field from Q1, Q2, and Q3. So there'll be some interaction, some potential that's set up between Q1 and Q4. So I'll call that U14. Some potential set up between Q2 and Q4. So I'll call that U24. And then Q3 and Q4. I'll call that U34. So I'm going to have to add all those terms to the sum. So basically what we have here is U13, and then we just said, okay, well, there was a U14, and a U24, and a U34. So just looking at this expression here, it basically, if you look at it for about a minute, you can see that basically what's happening is that what we're doing is we're basically looking at the interaction between each set of pairs, right? So Q1, basically there's three sets of pairs associated with Q1. So basically there's a Q1, Q2, a Q1, Q3, and a Q3, Q4. And then likewise for Q2. But we've already counted this interaction once. So, there's a Q1, Q2, and there's also a Q2, Q1. But there's only sort of one set of lines here. We didn't count this twice. So in general, what I can write this as, U total is basically 1/2, and I'll explain the 1/2 again in a second. The sum over the charges I not equal to j, qi v sub j at ri. And I can also just write that. So if I write what v sub j is explicitly, it's just 1/2. So again, I over j, or I not equal to j, k qi qj over rij. Okay, so let me just briefly explain that. So in essence, what we did when we did this configuration here is we noticed, okay, well, the total energy needed to assemble this collection of charges is basically going to be the sum between the interaction potential between each set of pairs, okay? And then we can write that as basically a sum where I is not equal to j, so you don't look at the interaction of Q1 with itself. That's basically what we're saying. We only look at the interaction between Q1 and the other charges in the system. And so basically, let's say if we looked at Q1, we had a Vj, which is basically, let's say, Q1 times the potential set up by 2, the potential set up by 3, that's this U13 term, the potential set up by 4, which is this U14 term, okay? And then the 1/2 is there because, there's a Q12 interaction, And there's also a Q2-1 interaction, right? But in effect, they're one and the same things. We don't want to count that twice. If I write the sum without putting the half in, I'll count the Q12 and the Q21. So the 1/2 basically just says, okay, well, let's just, we're going to basically not try to fix this double counting of the 1, 2, and the 2, 1. So we just put the half in, all right? And then this is just writing it out explicitly. So basically, it's just 1/2 times k, all the different permutations of qi and qj, where I is not equal to j, and the distance between ri and between a qi and qj. All right. Okay, so that hopefully should be pretty straightforward. And just physically, right, what you can think about is that it costs energy to make this configuration because, if you look at this configuration, basically you have a charge here, you bring in another charge. These are all positive. So they're actually going to want to repel each other, right? So as you bring in, let's say, Q4, it has to fight against the electric field set up by Q1, Q2, and Q3. It's trying to repel Q4. So it actually costs energy to bring this configuration together because basically the charges have to sort of fight against each other. And if you somehow let these charges go, they would all repel each other and fly apart. And we'll do a problem like that in your reading exercise. Okay, so now I want to move on and talk about, let's say, if we have a the voltage, how do we get the electric field? So I'm just going to set that up right now. All right, so as we talked about last lecture, we described, if we knew the electric field, which is, let's say these blue lines here, how do we get the voltage, going from A to B in going from, in moving this electric field? And it's basically just this line integral, E dot dl, where, dl is this path here. So how do we do the opposite? Like, let's say we already know what V is, and now, is there an easy way to get the electric field? And the answer is yes. So I'll basically just show you how we do that, okay? So VB sub A, as I wrote earlier, is basically the same thing as VB minus VA. Okay, that's just the definition of VBA. And that's just minus the integral of from A to B of E dot dl, okay? So there's sort of another way you can write this, right? Another way you can write this is basically just the integral of dV from A to B, right? So this seems kind of obvious, but if you integrate dV from, A to B, you just get the value of V at B minus the value of V at A, right? That's sort of the definition of an integral. So this would be VB minus VA. And that's going to equal to minus, and actually what I'll do is I'll bring the minus inside the integral. Actually, I'm just gonna erase this here. So so it's VB minus VA, and that's just gonna be this over here. So it's the integral from A to B of minus E dot dl. Okay. So, all right. So now you can look at something here and say, okay, well, these integrals from A to B are exactly the same, right? So if the integrals are the same, then the integrands also have to be the same. So what that implies is that dV must be equal to minus E dot dl, right? So what this is saying, if the integrals are equal, and the limits are the same for both of these integrals, then the integrands must be the same thing. All right, so then I can just write dV, and so E has some components, right? So I have this. I'll bring the minus sign over here, and I'm going to write E out. So that's just EX I hat plus EY J hat plus EZ K hat. And then dl is just, it's some sort of little path length, which has, dx I hat plus dy j hat plus dz k hat, right? So it's some arbitrary path length that, may have components in all three directions. All right. So then what I'm going to do is I'm just going to multiply this dot product out, right? So basically, you remember how to do that. So basically, we just take the I hat components and multiply them together, the j hat, and the k hat. So basically, this will be equal to ex dx plus e sub y dy plus e sub z dz. Okay, so now let's imagine that, so this is this general expression. So let's imagine we just take a small step in the x direction. Along x, and then, keeping y and z fixed. All right. So what that means is that dy and dz are going to be 0. So if we just kind of step a little bit, so our dl is such that we're just stepping a little bit along dx, then basically what we have is, minus dv dx is equal to e of x, right? And then likewise, if we, step along y, keeping x and z fixed, then we basically have pretty much a very similar expression, minus dv dy is equal to e sub y. And then the same thing for stepping along z, right? Keeping the other two fixed. Oops. And again, we got this because, right, when we stepped along x, dx would be the only non-zero component. These are both zeros, and then I just divide dv by dx. And you notice I write my derivatives like this. So this means a partial, the little sort of funny looking d means a partial derivative, which means that I'm only taking how the voltage varies with respect to x, and I'm assuming, y and z remain unchanged. All right? So basically I have this expression here where, e sub x is minus partial v partial x, e sub y is minus partial v partial y, e sub z is minus partial v partial z. And to write that in vector form, putting it all together, so basically the electric field is equal to minus the gradient of v. So again, v is a scalar. The gradient operation is a vector operation. So when you do this vector operation on the scalar, you get a vector quantity. So it basically looks like this. Minus partial v partial x, that's e sub x, I hat. So I'm just basically here, I'm just plugging in the definition. Oops, there's a k hat there. I'm just plugging in the definition of e sub x into here, e sub y into there, and e sub z into here. Okay, so this is basically how, in general, you get the electric field from the potential. This is the general three-dimensional form. If we just had a one-dimensional potential, let's say you just had v as a function of x, and you wanted e of x, then you would just take minus dv dx, as just a one-dimensional derivative. So you don't need to worry about the vector calculus. But this is the general three-dimensional form. And you'll have a little bit of practice doing that in your reading exercise. All right, so the last thing I want to talk about in this video is the concept of equipotential lines. Okay, so these are basically lines of constant potential, and just how to sort of read them and interpret them. So I'm going to go set that up right now. Okay, so over here I've just drawn a point charge plus Q. All right, and so let's consider, let's say some circular, or in 3 dimensions, a spherical surface around this thing, which has a constant radius, okay? So if we consider this ring here, right, then we can ask, okay, well, let's say we have a charge, an imaginary test charge somewhere on this surface, right? It starts at point A. And we move this test charge, anywhere along the surface to some other point B, right? So B could be here, B could be there. And we ask basically how much work needs to be done to move, this charge along this contour onto, let's say, any point on this contour, right? And so basically, so let's call this, so this circle is a constant radius r from the point charge, all right? So if you remember from before, the potential from the point charge, right, we can just write as V sub r is just K Q over R. So since every single point here is the same distance r away from the origin, all of these points have exactly the same potential, okay? So since all of these points have the same potential, it doesn't take any work for me to move a charge from here to there, because the potentials are the same, right? So in other words, so along the equipotential, which is that circle, then V BA is equal to 0 if B and A are on the same equipotential, okay? And you can imagine, so that this is for one value of the potential, so let's imagine, this is for, I don't know, plus 10 volts with respect to infinity. You could imagine some other equipotential surface, maybe this, blue line here, or this blue circle here. That might be an equipotential for another potential, which, maybe this one would be, be a lower potential because we're further away. So maybe that was like, plus 5 volts or something. All right. So what that means is everywhere on the circle is at the same potential 5 volts. Everywhere on this green one would be at the same potential, 10 volts. And so one, possibly familiar way to represent this. So let's imagine I'm just going to draw this in 2 dimensions. So we're just going to worry about the x and y distances away from the origin. So I'll try to draw my best, sort of 3D plot. So this is x, this is y. So our point charge is right at the origin. And so what we will get, and so the z-axis is actually going to represent our voltage, V of R. Actually, I'll use a different color for this. But, you can see that our potential is going to go as 1 over R. Oh, that was pretty bad. Boy. Oh, man. This is embarrassing. All right. We'll call that good enough. So, this is meant to represent the potential. I'm going to draw it out along the y-axis as well, so it'll do something like this. And so this looks a little bit like, it's supposed to represent something like a contour plot, right? So if you ever looked at a topographic map, this is basically, you basically get these sort of rings. You get these sort of, these contours that are supposed to represent, elevations that are at the same height, right? So in this case, if you were going to look at a contour plot of this potential, it would look like rings. And these are supposed to be rings that are sort of centered around, x and y is equal to 0. And so the way, you can kind of read this is that, this ring here is at a higher potential. And, again, if you use this sort of mountain analogy, right, it doesn't really take you much work, much effort to walk around if you're on the same level. So if you're sort of at a ridge here and you're just walking around this ring, basically you don't have to do much work to move around the ring. But, to climb up to a higher ring, you have to put a lot of work in. Or, if you wanted to roll downhill to a lower ring, you would pick up some kinetic energy, right? So it's the same sort of idea for these equipotential surfaces. So you can just really think of the equipotential surface as being very much like looking at a topographic map and saying, okay, obviously I have to put a lot of work to get to the top of the mountain. I have to, go up. But if I'm on, sort of one ring, if I'm on sort of one contour, I can sort of move around that contour very easily because I don't have to change elevation. Or in other words, I don't have to change potential. All right? So another thing that's interesting about equipotential surfaces, so again, I'm just going to change the color here. So on an equipotential, where B and A are on the same equipotential, we just said V, B of, So V, B of A, if they're on the same equipotential, is basically minus E dot dl. And if A and B are in the same equipotential, then that's 0. Right? So E, on, for some arbitrary potential, or, E is not necessarily 0, right? E could be whatever it is. So that implies something about E dot dl. Basically what this is saying, and, this is true for any A and B I pick. So it could be from A and B here, it could be A and, it could be B over here. So, it doesn't really matter what the endpoints of A and B are as long as we're on the same equipotential. This integral is always 0. So basically, since this integral is always 0, basically this implies that E dot dl has to be 0 everywhere on that contour. Right? And since dl is basically taking the path of that equipotential, taking the path of that contour, the only way that can happen is that if E is perpendicular to dl everywhere in that potential. So basically, in other words, E is always perpendicular to an equipotential surface. And you can see how that's certainly true for, the case of the point charge here. So the equipotential surface is this green line, and we know that the electric field comes out radially from that, right? And then you can automatically see that, okay, well, the work done in going from A to B has to be 0, because at every point on the trajectory, E and the electric field, which is the black line, and dl, which is the red, are perpendicular, so their dot product is always 0. Okay? So we know that E is always going to be perpendicular to dl. In which direction does it point? So the guideline is basically that the electric field E always points from higher V to lower V, okay? So always... Or in other words, to take the sort of, topographic map mountain analogy, if I had a little mass here or a little test charge and I let it roll down the mountain, right, it's going to go that way. It'll roll downhill, and that's basically this. And so the object is going to roll downhill, and it's going to roll in the same direction the electric field is pointing, right? So you can kind of think of it, the electric field as sort of pointing, away from, for the point charge, it's pointing away from the origin, right? If we were going to consider a negative charge, then this would be inverted. So instead of being like a mountain, it would be like, a sinkhole or something, right? It would be a big hole in the ground, and so this would just be inverted. And in that case, the electric field would be pointing inwards because, if we imagine we put a little test charge on here, a little mass, it would roll into the hole, right? So for example, a very quick example would be, if we had infinite parallel plates, what would the equipotential look like for that? So imagine we have a top plate and a bottom plate, and these are infinite. So I'll draw some arrows out like this. So let's imagine the bottom plate has some positive charge density plus sigma. The top plate has some minus charge density minus sigma, right? And so from what we've learned before, there's some electric field that points from the, we did this before when we were talking about Gauss's law. There's some electric field that points from the bottom plate to the top plate. So this is what the electric field lines look like. So they start on one plate and they terminate on the other. So then in that case, what do the equipotential lines look like? Well, they'll just look like this. They'll just be exactly parallel to the plates. And you can also see they're going to be perpendicular to the field lines. Here's one line, here's another, right? And you can see here, right, again, talking about if I have to move a charge from here to there along this equipotential surface, it doesn't take any work, right? I'm cutting parallel to the field lines, and we kind of learned earlier that, if I move, if I have this infinite parallel plate and I just move perpendicular to it, that's not going to cost me any energy. It only costs me energy to go from, let's say, the bottom, from the top plate to the bottom, right? But moving laterally doesn't cost me any energy. So we could define, let's say, this, bottom plate to be at some potential plus V relative to the top plate, which we'll define to be 0. Okay. All right. So that's enough for talking about equipotentials, how we can sort of interpret field lines based on equipotentials, the movement of charges in sort of equipotential surfaces, and basically how to get the electric field from voltages.